Hello everyone. We are on day 12 of our challenge of doing 30 deep learning projects in 30 days. So the problem is about, yeah, so we can see it from the list. The problem is to implement YOLO, you only live once, I believe, for object detection. So the tutorial for YOLO is this. Uh, It is a real time object detection. You only look once. Okay, so here YOLO means you only look once. Is a state of art real time object detection system. On a Pascal triangle X, it processes images at 30 focal points, focal per second, focus per second, and has a map of 57.9% on a COCO test depth. I can go ahead and read it, but I will not understand much of it. It says that it is extremely fast and accurate. What I'll do, instead of going through this tutorial, not here, yes, instead of going through this tutorial, I am thinking of going with the set flow for solving our problems. I'll go and ask ChatGPT to help me with the problem, right? I will use the same context window as I have used for our previous problems. So let's start. I'll copy it and say, hey, it is day 12, and here is the problem statement. Okay, let's wait for it to generate everything and then we will start with it. It is going to be a little different from what we have explored so far. So we have been doing adding convolution layers and all to our sequential model, but it seems a little different code wise. Yes, so it is going to be a little really interesting. I guess this is part of computer vision. So yes, it has generated. So let's go come here and start. It says that okay, fantastic. Day 12 challenge is about implementing YOLO, which is you only look once for object detection. YOLO is one of the most well-known, widely used real-time object detection module due to its efficiency and speed. Since this is your first time diving into YOLO, we'll take a tutorial based approach on understanding the concept and getting a simplified implementation up and running. Okay, so this is we'll take the tutorial based approach and focus on understanding the core concepts and simplified implementation. Of course, because this is my first time. And yes, YOLO, it says that YOLO, an overview of YOLO is that it stands for you only look once. It is a popular object detection model that can identify and locate multiple objects in a single image with a single forward pass. Okay, with a single forward pass in a single image, it detects and it identify and locate multiple objects. Okay, so it is an object detection model. Here it says, if we go to the example, here in the example of this tutorial, we can see it has very nicely detected an object, a cycle, a dog, and truck, which is really cool. It works by dividing an image into grid and predicting bounding boxes and class probabilities for each section of the grid. Okay. And then YOLO version 3 versus YOLO version 4 are popular versions, but not versus version 3 and YOLO version 4 are popular versions. But in the recent times, we also have a YOLO version 5, which is the most approachable for beginner due to its simplicity and open source implementation. Okay, this is an open source implementation, and it says that it is good to start for the beginners. So I guess I'll go ahead with this one. We will use a pre-trained YOLO model to perform object orientation detection. Okay, we are going to use a pre-trained YOLO model instead of training YOLO from scratch, which requires a lot of computational power. I'm running a basic Mac, So I think I don't have that much power, computational power. So I'll stick to, instead of training the YOLO from scratch, we will use a pre-trained YOLO model and run it on a sample image or video. Okay, we will use a pre-trained in YOLO model because we don't have that computational power. Steps to implement. Uh, we will use YOLO version 3 and version 5 or version 5 depending on the simplicity and available resources. Okay. The easiest way is to use a pre-trained model and perform inference on sample images. Okay. We can use OpenCV library with a pre-trained YOLO version 3 model. Okay, we are going to use OpenCV library on a pre-trained YOLO version 3 model. Okay. First, let's set up the environment. We will need OpenCV, YOLO weights, OpenCV to load and display the images. We will need YOLO weights and configure files. Then we will need Python packages like NumPy for general processing. So let's install that. Let me clear the day 11 thing, and let's do what? Yeah, install. Pip install. What do we need to install? OpenCV Python, OpenCV Python headless, and NumPy. I guess I do have NumPy already installed, but let's yeah, install it anyways. If I do have it already, it is not going to install. So yes, it has installed the OpenCV Python headless 4.10 successfully. So good, we have it now. Now we are going to download the YOLO weights and configuration. YOLO version 3 uses two main files. The weight files. This is YOLO v3.weights, which contains a pre-trained parameters. Pre-trained parameter. Okay, so it is going to have two files, one weight file and configuration file. The weight file defines the pre-configured, pre-trained parameters. The configuration file that we will describe the architecture of the YOLO model. Okay, so we can download. So it is not clickable. Instead of relying here and then getting stuck with the wrong file, what I can do, I can ask ChatGPT to give me the link explicitly in the form of string so that I can copy and paste. Also, need before that, let me read this line also. It says that we will need a Coco dataset class name coco.names file which contains the name of the 80 classes that YOLO version 3 is trained to detect. Acha. Okay, so we also need to download this file which is the okay which contains 80 classes that the model is trained on. So let's download that. Download it. This is not downloadable, so we are going to ask it. Instead we can, I guess this is there in this data set, right? We can get the file from here itself, right? Data data coco.names configure darknet. What else we do we not need to download? The weights, right? Weights, not data configure. If I see I do not have the weights, so I'll ask. Instead of that, let me download what I have for now, the configuration and names file. So I'm going to download it, download it, move it to my what folder? YOLO version 3 folder. So I'm going to create a new folder called YOLO version 3. YOLO version 3. So I'm going to move this YOLO, not from download folder, YOLO version 3 config to our YOLO version 3 directory. And then we need to download the move. Sorry, we have downloaded the coco.names to our YOLO version 3, and done. And let me, if I am going to land on the same thing, this, okay, um I'm going to see, I cannot download the from your link. The link is not clickable. Can you please give the link in string form wrap with, if that way it is not going to right, it's not going to convert it into non-readable thing. So yes, I can. Oh, this was the correct, I guess. Patrick 013 object detection. No, yes, I was in the wrong. So yes, we can download the weights from this location. Uh, Now coming back to moving this thing also, download YOLO. It starts with what file? Uh-huh. Let's see. Okay, it is still downloading. Let's wait for it to download, and then meanwhile we can read this step, which is to implement the YOLO for object detection. Here's the Python code that implements YOLO using OpenCV. So here we specify the weights path and weights config and names path, names file path. Then we open the hmm, detail explanation is that we with we open the names path, this coco names read only. We store the class names. Then we load the YOLO model from the config path and the weight path. We use cv2.dnn and read net from darknet. So what does it do? Read net from darknet loads the YOLO configuration and waits file. Okay. This initializes the network and prepare it for inference. Okay. Set the model to use CPU and or CUDA if available. Comment if only CPU is used. So I have downloaded. First I need to move the YOLO weights to our YOLO. And now if I see, I should be able to see these three files in my YOLO version 3 directory. So I have it. Now let's start and go to each piece of code line by line, and then yeah, then be done with it. Learn something new. Yes. So let me go and minimize the terminal and create a new file, day12.py. Add it to our Git repository. Mention what the problem is about. Problem is that we are exploring YOLO for the first time. So the implement YOLO for object detection. The let's mention the file link for each files. First, we are going to config file weights file. Weights file will be from this, and YOLO version 3 and YOLO version 3 YOLO version 3 coco.names files. Why do we use it? Because we want the labels for each of those. How many? 80 categories. 80 categories. Yes, we have everything. Yes, let's start. So I'm going to import the libraries. Open CV2 and then import numpy as np. Then we are going to load you only look once version 3 weights configuration and coco class names duration and coco class names. So how do we do that? We define the weight path is going to be, okay, if you're mentioning it here, I don't think we need to mention it here. Sorry, here we mention the data set and it is there in the, not data set, it is there in the YOLO version 3 and weight, sorry, YOLO dot version 3 dot weights. Then we have config path, configuration path is YOLO version 3 slash YOLO version 3 dot conf cfg. Then we have coco names dot path we have inside YOLO version 3 slash coco dot names. Done. Now we are going to load the coco classes names. So with open I think I'm not that familiar with using the OpenCV. I might do a couple of like 10 something problems on OpenCV maybe after completing this challenge so that I become familiar with this OpenCV. Dot f read the file, this f file, strip, yeah, strip the ends and then split using the next line. Once done, we have the classes name. So let's print the classes name. Now let's go and run this file. Say I, not here, I'll say python day 12 and we can see the classes name here. So it is working fine. Now load the YOLO 3 version 3 model. Load the YOLO version 3 model. So let's lower caps it. Now let's do that using the read net from darknet and pass the configuration file path and weight path. So we have cv2.dnn.read from darknet, mention the config path and the weight path. Done. We have loaded the YOLO model. Set the model to use CPU or CUDA if available. Comment if you only have comment if only CPU is used. Let's look at the description first. I'll say, can you explain each line of code I'm simply going to ask to explain me the meaning of each line of code. So we are mentioning what CPU to use. Comment that if we have to comment it out if only CPU is used. So we do not use it. Now it says load the input images. Replace. This is better. Okay. Let's go back. We have understood it. So it says yes. We have loaded the YOLO object pre-trained load, which is going to load with the weights and the configuration file. The pre-trained network for object action. Okay. Read the configuration weight files and load the pre-trained network of object detection. Okay. Then we set the preferred device for configuration. Use OpenCV's backend and run on CPU. If you have GPU, you could use Coda for faster. Okay, faster processing. We say that use CPU. Okay, we can use OpenCV's backend. So I guess that we need to mention here. So we mention it with the help of set by backend and target device. So how do we do that? First fix the typo, then we do net dot set preferred backend, preferable backend and preferable target. Set preferable backend, and it is cvn dnn dot dnn backend opencv cv2 dnn. uh, it is dnn backend opencv. Use the opencv as the backend, then use set preferable target. It is going to be dnn.cp. It is dnn target cpu, dnn target cpu, this one. Once done, we will come back here. When then we will load the image. We will load the image. uh, can I download an input image? Can you give me an input sample image for testing? Let me ask ChatGPT only to give me the sample image. Why to download it from an external source? Okay, my model is ChatGPT 4.0 with Canvas. If I would have used ChatGPT 4, then I can maybe download. What I can do, I can, I can, I can explore ChatGPT and search. Give me not GPTs. I'll say ChatGPT and close it here. Give me an image with a dog. The image of a that contains a dog, cat, and a human. Oh, nice. We have a uh, dog, cat, and an image. Nice. I guess that's what people are using in. If we see YouTube videos, people are using a lot of images like this to describe a story. So this is how they are generating the image. Really cool, no? So yeah, we have an image. Let me download. Have I downloaded this image? Yes, I have downloaded the image. Let me move the image from downloads folder and Dali E to our create a new folder. Let's create a directory images images and sample images. Uh, if I go here, I see the image. Let's rename it to uh, dog, cat, human. Oh, nice. Clear it. We have the image. Now, if I open it, it says I can, yeah. Yes. Uh, I have I have an image in WebP format. Will that work? Let's see. Okay, as long as your version of OpenCV has WebP support. Okay, so we will go ahead with WebP only. If it will not work, we'll replace it. We'll just go and convert it into a JPG image. Okay, so let's come and load the input image. Load the input image. Say image cv2 dot I am read, which is for image read. Mention this name of the image and get the hit width and height and width. Sorry, I am read. We'll mention sample images slash dog cat human webp. Height width of the image. Let's get the image height and the width dot shape and to yes. I'm curious to see what is in the image dot shape looks like. Let's run this script again. The image looks script the image This image looks like, the shape looks like 1024, 1024, and 3. Okay, 1024, 10. So okay, from so it has, I mean, 3 is for channel, so this is 1024, 1024, which means height and width. So height is 1024, width is this. Then we will do this. Done. Extract the height and width of the image for later calculation. Okay, we have generated. We are done with the step 3. Now we are going to create a blob from the input image. So cv2.dnn blob from the input. Blob is a format. Big. If I tell you blob, not this. This is something. Uh, Format. Binary large objects. Is it, so I guess that is blob. What blob is here, I believe. So converts the input image into a blob that model YOLO model can work with. Okay. So it normalizes the pixel values from 0 to 256 because they are in RGB, to 0 to 1 because model is good at training when the range is lower. Then we reduce the size of the image from 1025, whatever the size was, to 416, which is required by YOLO. Then we swap the red and blue channels since OpenCV reads images in BGR, which is, yeah, okay. It reads in BGR, not RGB. So we are going to swap R and V. So we mentioned that. And then we crop. Do we crop? We mentioned this crop also. Yes, we do not want to crop. Okay. Once done, we pass this blob to our YOLO network. So let's do that. What we are going to, creating a blob from input image, creating it create blob from, not blog, blob from input image. I'll do this so that I can always see the changes here, not at the bottom. Yes, let's do that. Blob, not blob. cv2.dnn dot blob from image. The image is this. Then we have to mention the scale factor. We have to normalize it to 1.255 to 0 to 255 to 0 to 1 range. Then we want to resize it, so we'll say which parameter, size. Resize it to 416 into 416, which is required by the YOLO version 3. Then we swap R and G because the YOLO expects in BGR, not RGB. Then we mention crop. No, we won't be doing that because it is not required in the case of YOLO. Otherwise, ChatGPT would have mentioned it. Then we add it to our uh, YOLO network. So this is blob. Mm, let's getting output list. So once we have done that, we have set the input to our YOLO network. We now have to configure the output layers. Okay. So the YOLO dot get layers name will give us the layers name, and the output. So it will return the name of all the layers in the network. Okay. The get unconnected out layers for in and net dot get unconnected out layers. Print the output layer name. Okay. So it will return the output layers. Okay. It will return the output layers. This will return all the layers. Now creating a list of the output layers name that will be used for making prediction. Okay. So we need to create the output layer names. Okay. Why are we doing this? Let's say let's do this. Let me print things one by one. We saw that already. So we are doing it, getting output layer names. Get output layers name. Not out output layers name. Then say layers name will be net the model dot get layers name, print layers name. Let's run this file again. The layers name is like this. Do we have print anywhere else? No. So the layers names are like this. So the convolution layer 0, bn1, binary layer, leak 1, con 1, BN1, leak 2, leaky 2, contours. We have so many layers, so it has printed the layers. Now we use this net dot get unconnected out layers. So we'll say, let's print this net dot get out, sorry, unconnected out layers. This is what it is using, right? Let's see what it will print. We see what is there in the layers name. Now clear the terminal, run it again, and we have these many layers. Oh. So the output layers are this, with this index 20, 27, 200, 227, 254. Okay. For I in this the output layers, it returns the indices of the output layers. So the indices of the output layers is this, and for each index we need to get the output layer name. Okay, so layer names. Okay, I'm very stupid. So this thing, let me, for uh, index in net dot get unconnected out layers, which returns the output layers index. Um, this is output layer index. We'll do what? Layers name. Since this layers name is an vector, which ranges from, the index starts from 0, so we need to minus it. So we'll say minus it. Okay, let's print it. Why is it doing I index 0? Print output layers index. Let me run this. 227. Okay, correct. And why are we doing, I'll just ask here. So if I'll do layers name, layers, sorry, output layers, sorry, just a second. Just a second. Let me reuse it. Let me refresh it. Yes, let's come back to check number, output layers names 8. So it says output layers index. So 0. If I'll do this, so it does not make sense, right? Why are we doing it? Let me copy it and then paste it, and then print print I 0. Let's run it. Let's get it. Let's run it. Let's not do this. Let's do this. That's what it was doing, right? Layer's name, yes. Let's do this. Let's comment this. And Let's run this. It says we have an error in line number 39. Uh, Invalid index to scalar variable. Correct. It should be I minus 1. Right? If it is, yes. Here I'm going to ask. It is really confusing. Here, why are we doing? Let's understand what it says. In order to, okay, for instance, get this will return this. Okay, this is what it is. No, it is not returning this. It is simply returning the ith value. I in this case will be something like that. No, it is not. So it is returning that, not that one. So it is returning this. This is what is returned by unconnected layers. Got it? No, that's why we do not need to do. Uh, these are one base instances, meaning they refer to 20th array, 22, 27th array, 50th array. Adjust the index of the. Here we use a I minus 1 for each I. Okay, that's why we are minusing that. Okay, okay, let's do that's minus. I understood, right? So clear it. Yes, yes. Now we have the output layer's name. Print output layer's name, and let's run it. We have YOLO 82, YOLO 94, and YOLO 106 as the output layer's name. Let's mention it here. Let's comment it out. Let's go back. Let's go back. Let's go back. Not this one. Not this one. Not this. Yes. Not this one. So yes, now we are done with the step number 8. We will now go and do the step number 9, which is not step number line number 9, which is to perform forward pass. This net dot forward performs a forward pass through the YOLO network using the net input block, which produces the detection for the input detection, which produces the detections for the input. Okay, forward pass means it is going to get the detections from the input images. Okay, I'm just trying to understand what are we doing. Uh, I'm going to ask here, what is the meaning of forward pass? If there could be a way to minimize the responses or some of my questions, it would be great. So yeah, it says forward pass is in the context of neural network, and deep learning refers to the process of passing input data through the model in order to get the predictions. In simpler term, it is the act of feeding data through the neural network to compute the output. Okay, which is in case of YOLO includes the object detection. So forward pass is we are passing the input data to get the detection, to to get the output. So it will pass the input image. It will process by YOLO model layer by layer. We saw all the layers it has, and then it will give us the output, final output. So this includes bounded bounding boxes, confidence score, class probability for each object detected in the image. We will not go and understand what is happening inside the forward processing, because it might overwhelm me, which is not required for this problem. I just want to get introduced to it. So yeah, so I understand that forward pass is the process we put in the input image, like the convolutional neural network. We saw it has many layers. It also might have layers. We saw how many layers it had, like we saw in the layers names. So it will apply those layers and it will produce the output. So we are going to get the output. So let's do what? Perform forward pass. So layers output. We have got the detection outputs from net dot forward. And here we pass in the what do we pass it? So we pass the blob. First we convert the image into blob. Okay, first we load the image, convert the image into blob. We put pass that blob to as input to our network, YOLO network. Then we get the names and the output layers names and the layers name, and then we simply pass the output layers name, and we get the layers output. Here we print the layers output and see what this line is doing, and we have an error. Clear. Let's run it. We have an error. We have an error here. It says the layer, the for pass inconsistent shape of concat layers in the function. I don't think we might have to do that also. Oh, that was required. So if I run it, if I comment it out, will it still? Okay, I'll say I getting an error on line 9. So ours is you can manually set the output layers name if you know them. Typically YOLO version 3 they are YOLO 8294.106, YOLO 8294.106. So it is correct. Correct. However, session might be very slightly running. We have the same name, right? So it is good. Hmm. Swab RB true. Are we doing swab RB true? Yes. Crop false. 416 1.01 divided by 2 point. It is same thing, but I'll do it anyway. Scale factor. It is scale factor, and then we need to pass the image. Need to upgrade the OpenCV. Let's upgrade the OpenCV. We have done that. We can pass set the size to be 608 608. It is made up of many layers. Some layers involve concatenation. It says timed out. Let's run it again. I have even advanced version. It was asking to install 4.10, 4.5. I have 4.10. So the version is not an issue unless the upgraded has deprecated this code. Hmm. It has different height versus different width. Let me go. Could be a reason that I have downloaded a webp image. Yes, fact that your event could potentially contribute to the problem. So what we can do, we can load the image, of course. Let me do what? Let me go ahead with using a simple image. Let's not experiment it until we know what we are doing, right? So I'll go get the image suggestions from this only. If you remember, gave me some suggestions to download the image from. So I'll go get the image from this. Access night. That also has access night issue. Mhm. Animals in wild. Let's see. Animals in wild. Test YOLO version 3. I can maybe use it. YOLO version 3 image. Test image. Test image. We are here back to this thing. It is detecting the image really nicely. Can I download the image? We can download the image from. Sample JPG image for image YOLO. Let's rely on Kaggle. Kaggle is a really good source for everything, I guess. No data. So there is this image. Let me download this image and let's download it. Let's save this image. Test YOLO. Let's not go here. Let's go here. Move. Download test YOLO to our sample images, and it is a JPG image. Let's do this. Let's run this with the test YOLO, and now let's run it again. Not this command, but this, and we have the error again. Oh my god, we have the error. Let me go and fix this error. What I can do, maybe I can fix this error, and then you guys, once I do that, I can continue recording this video. Mm. Now I have this. uh, I have replaced the image with an image I got from a from Kaggle. Now I get this error. We can also use 602 608. Let me try that, if that will work good. Thank God. So that is working. I'm now really curious to do what? To replace this with our WebP. So I'll say 608 and I'll clear this, run this, and it is working fine on our previous image also. Chalo, good. It is good. We resolve this error. Okay, let's go back to our steps. Go back, go back, go back, go back, go back, go back. Not here, not here, not here, not here. Yes. So let's do what? Let's print the output layers. Let's print the output layers on our original image. So yes, the A layers look like this. Now we will do what? We will initialize list of detection results. Holds the coordinates of the bounding boxes around the detected objects. So this will hold the bounding boxes around the detected objects. Okay. Hold the confidence score of each detected object. Okay. And this will hold the class's ID of each detected object. What do I mean with that? If you remember, if we go here, YOLO, and YOLO real time object detection, if we see the this result, we see some classes like what is this image, what class it belongs to, what is the score, detection score, and then the confidence. So all of that we are going to, the detection results we are going to store. So we are creating initializing list for them. So let's go and initialize list for detection results. Comment it out. Let's move it. Yeah. Initialize list for detection results. So what are we going to do? We say boxes and empty to hold the bounding boxes. Confidence confidence to hold the confidence score. Then class id, the IDs of the class that they have detected they belong to. Then looping over each output layers detection. Okay. Now, if we do that, this loop through all the detection provided by the YOLO model. So it will loop through all the detection provided by the YOLO model. We saw, if I maximize it, this is all the arrays, the output layers look like. This is the predictions for each class. Like if I want to see, let me see. If I want to see the first layer, output layer, so clear it and then run this again. I should see that it has how many classes it has. It has 80 classes. So if I see the shape of it, so it should have 85 columns and 1083 rows. Okay, so this is the probability of each class, right? So layers output. Now I'll do what? So loop through all the detections. Now we get, for detections in the output, for detection in the output, uh, they did our detection in the output. The detection 5 gives the class code after the five bounding box parameters. So five are the bounding box parameters. Okay, that is why we had 85, because the five columns are for the bounding boxes. So score class id is the maximum from the scores, that is all the 80 columns except those first five columns. We the rest of the 80 columns are for the 80 classes, the probability of 80 classes, and then we are going to get the maximum probability, and that is going to be the class id. The index is going to be the class id, and then we will get the confidence, the value, the confidence value from that score. Okay, so I do understand that it is pretty easy. Why? So we'll do what? For output in layered outputs, for detection in for inside each layer we are going to do detection. For detection in output, not output, the scores for each class is going to be from detection. Remove the first five, because five are saved for what? Five are saved for the bounding parameters, right? And then we have this capital, and then we have scores. Then we are going to get the class id. Class id will be the class id numpy dot argmax, maximum from this vector, scores vector, return the index, and then confidence. Confidence will be the score of this class, the maximum class predicted, the class that predicted it with the maximum probability or maximum score here. Okay, now filter low confidence detections. Okay, if the confidence is greater than 0.5, then the only consider the detections with confidence. Okay, now it will give a lot of confidence, lot of detections. Now we are going to store only the confidence which are actually has good score. So all the confidence greater than 0.5 are going to pass through, otherwise we will not store them, we will not keep them. So only consider detections with confidence greater than 50%. Okay, detection 0 to 4 gives the coordinates of the bounding boxes. Yes, we saw that. Center x, center y, width, height. Okay. This is center x, center y, width, height. And this np dot array will be width, height, width, height. Scales the bounding box to match the original image size. Okay, it will scale the bounding box to match the original image size. Okay, understood. So we are doing filtering low confidence, and then getting plotting the getting the width, height, and box width, center y, center x of the boundaries. So confidence if confidence is greater than 0.5, then only consider it, and we'll say the box is will be detection. Now from the detection, get the first four only, which are width, height, width, which are center x, center y, width, height, and multiplied with the width, height, so that we get they scale up to the original image size. Multiply np dot array width, height, width, height, and wrap it around the pieces. Then we have center x, center y, box width, what height. Get these things from the box. Uh, Center x, center y, width, box width, box width, box height, HEIGHT, center x, center y, box width, box height, box dot get the int values converted into int. Then calculate the top left corners coordinates, and then we will save the detection. Yes, almost. We are almost done. Calculate this. Now we are going to calculate the top left coordinates. They all are inside the right. We get the top left coordinates and save the box in confidence and class IDs. So we get the top left corners. At the top left coordinates, we do x is equals to int, typecast it to int center x minus the box width divided by 2. Y will be center y box height divided by 2. Once done saving the detections, we will save the detections. Save the detections boxes dot append. So the boundaries we need to append x and y, the top left and right corner, the width and height. So it is going to be x, y, and box width, right? And box height, correct. Then we will append the confidence also. Confidence is dot append the floating value of the confidence. Then we will append the class IDs. Class class IDs dot append class ID. So yes, we have saved everything here for only for those confidence, for the confidence with value greater than 0.5. Once done, we do what? Just a second. So we are done with what step? We are done with, if we come here, looping through each layer. Now we are done with detecting the detection step. Okay. Now we apply non-maxima suppression to suppress weak and overlapping boundaries. We are applying this non-maxima suppression. We are applying a suppression to suppress the weak and overlapping boundaries. Okay. We further apply the suppression where we mention. Let me come back here. So here, the NM boxes applies non-maxima suppression to remove overlapping bounding boxes. So we might have overlapping bounding boxes. Okay, so it will separate them. This function suppresses them using non-maxima suppression. This score threshold 0.5 is the minimum confidence score to consider that we had used earlier. And the NMS threshold, this non-maximum suppression threshold, how does it decide what to keep and what to suppress is with this threshold. So how does it decide whether two boxes are overlapping or not? With this threshold, it decides that. So use non maxim maxima suppression to what? To remove overlapping boundary boxes. Okay, so we'll do what? Indices of the overlapping boundary boxes, dnn.nm boxes. We mentioned the boxes that we had identified, list of the boxes. Then we mention the confidence, and then we get the score threshold, that 0. 0.5 at least confidence value to consider, and the overlapping threshold will be nm threshold 0.4. Once done, we draw boundaries and labels. Now we are almost done. Draw boundaries and labels. So we'll do down boundary boxes and labels. Yes. For I and indices flatten, we flatten the indices, we get the x, y, width and height values, and then we do what? Let's look at the boxes. Before that, let's just visualize the boxes. Boxes print confidences, and let's run it. Boxes are like this. These are the coordinates of the boxes. These are the coordinates of the boxes, and this is the confidence value. Okay, we have these many. The YOLO model has identified these objects, these many objects. So let's iterate through each object and get the x, y value, the first and second, third and fifth. So this is the width, x, y width, height. Okay, so we'll do for indi for I in index in indices dot flatten. No. We have applied suppression also. No, so let's, after suppression, let's look at the indices. Let's look at print indices. So let's comment this. These were the boxes, these were the things, and these are the indices of the what? Of the boxes with threshold value and score value more than this and this. Okay, so we will have to iterate through index and indices, and let's flatten it. Why do I need to flatten it? I don't think I need to flatten it. I guess this will work. This is already flattened. So we'll do what? The x and y will be boxes I, the first this first uh, row element, 0, boxes I index 1. Say suppressed indices, suppressed indices, and we are iterating through that. And then we have width and height. Width and height is going to be the second and the third index. So boxes index 012 boxes index 0123 we create a color object of 0 to 550 RGB, channel RGB. Then we create a rectangle of these coordinates on this image XY, and then the X and Y, and then the other X1 Y1 X2 Y2, and the color we mentioned, and then this, and then we create a rectangle, and then we mention the class name, the class name as in the confidence score, and what object it is, if there is a cat or dog, what it is. And then we put the text, this image text, everything. So we do that. So let's do cv2 rectangle, create a rectangle on the image, and then we have x and y, x1 and y1, and then we have x plus width, y plus height, and then we have color, and then we have text. The text is the confidence, so we will text output text as the confidence score, and the class it belongs to, so it will be class. From the class names, get the class id of this index. So from class, if you remember, we got the class names here, right? This, so we are going to use this variable class names, and then we have got the this class ids. Okay, and then from here get the class id of this index. Once done, so this is one, so it will may represent as dog with confidence score, confidences of this index, and mention it in float. Yes, once done, we just put the text on the image. So in the image, put this text, where do we want to put it, on that x axis, and y minus 5 maybe below the image, and this is the position. Font will be, this is going to be the font, and the other things, cv2 font italic, I'll say font italic. This is the size of the font. Font scale, and then with this color, and then this, then thickness is this. Okay, so this is thickness is this too, and thickness is this, color, font scale, what font and everything we have mentioned. So it is going to put the boxes on the image. Now just display the final image. We are almost done. So we are going to display the final image. Display, not display, play the final image. So we are going to have three functions. First is I am show to display the output image with this text, with this title, and then we waits for a key press to close the window. Don't wait for a key. So with any key press, it is going to close the window, and then destroy all windows. So I'll say dcv2 I am show text YOLO image detection, and this is the image. cv2 wait time, wait key is 0. Don't wait for when someone presses the key to exit, and then cv to delete, not delete, destroy all window. Now let's run and hide all of that. And yes, let's clear the terminal and run it. Oh, see, so it is a cat, it has protected. It is a bottle, it is a book, it is a person, it is a dog. Nice, it has detected many things here. Really cool, no? Let me take screenshot of this. And yes, I've clicked, or I've clicked anything, like I have clicked D, and it has exited and destroyed the window. So really cool. I'm really happy with how it has turned out, and I always used to wonder how people are creating these things. So now I know there are pre-trained models that we can use using OpenCV to execute such things. So I'm feeling really happy with something like this. So yes, we have done a great job today. Use YOLO, a pre-trained real-time object detection model, configured it with an image that we had generated using. We asked ChatGPT only to generate this image. We saw little some challenges, but yes, today is a great day. So I'm going to add the image. I'm going to add this, not this. I'm just going to add this code to our repository. Add code for day 12 YOLO image detection day 12 code, and this is day 12. Push it to main branch, and we should be able to see the day 12 changes here, the file here. So yes, you guys can go and get the source code of all the problems from this repository. We'll come back, and I'll then solve the day 13 problem. So I'm really excited now. We are going to uh, pick up the problems related to computer vision, and it is really exciting. So thank you very much.